Okay, so it is time to start. So let us start. So before we begin, let's see if there is any question from the student. Anything? So how was the recitation session yesterday? Was it okay? So you guys discussed about this fixed point theorem, I believe? Yeah. So was it clear enough? Yeah. Okay, good. So today is the last day of the lecture, and then so hopefully I will finish what I intend to cover in this lecture. So quickly go over what we discussed yesterday. So yesterday we first derived the equation for the conservation law, and from there, by considering this flow motion of ideal polytropic gas, so we derived the equations, so-called Euler system for compressible flow based on three fundamental conservation laws, right? So what were they? There was conservation of mass, momentum, and energy, right? So for simplicity, we assume two-dimensional flow, but still the equation was complicated already, right? So in order to just simplify the problem in a way that we can handle, so we first remove the time variable from the problem so that we get the steady Euler system, right? And after that, in order to simplify further, so we assume a lot of conditions, such as the Bernoulli's law, so B equal to B0 for constant B0, and the isentropic condition, so entropy is globally constant, right? And in that case, so we actually show that if the entropy is a constant, so we have isentropic flow, then the vorticity of the flow becomes 0, right? Which means that the curl of the velocity vector field is 0, so that we can finally represent the velocity vector as a gradient of a potential function phi, right? And then once we are at this point, so here the phi is a scalar function, so this is going to be a two-variable function because we are considering the two-dimensional flow. So this is a function from R2 to R, right? So that if you take the gradient, it's going to give the velocity vector field, right? So we call this phi velocity potential. And then now we can finally write down the equation for this potential flow equation in the following form. So we have divergence of so B0, which is a Bernoulli constant. So 1/2 grad phi square and 1 over gamma minus 1 grad phi equal to 0. So where here gamma is a constant given from the problem. So physically it is called adiabatic exponent. So that is the equation that we derived yesterday. So obviously this is a second order PD. So when I say second order, it means that the highest order of the derivative of the function phi is 2, right? So we have to be able to differentiate the function phi twice, right, for this equation. So second order, the nonlinear, so obviously this is nonlinear, and we discussed why this is nonlinear yesterday, right? So this is the second order nonlinear PD, but most importantly, this is the type of this equation is not single. Actually, it is a mixed type. So this is the interesting point that we want to look further today, okay? So what do I mean by it's a mixed type? So now we are going to carry on a further computation for that. So just to simplify the computation further, now we are going to assume that here, so for simplicity, so we are going to assume that the constant B0, which is a Bernoulli constant, is going to be just 1, just for simplicity. And for gamma, so gamma is just a given constant bigger than 1. And for simplicity, we are going to just look at the case where gamma equal to 2. Well, generally speaking, people are more interested in the case where gamma is less than 2. But for computation matter, so this is much simpler to handle. So I'm going to just to focus on the case where gamma equal to 2, okay? Then this equation becomes, so divergence of So 1 minus 1/2. This one, and this is simply 1. So really, you can see that this is really simple, right? And times gradient of phi equal to 0. So now, so this is the equation that we are going to focus from now on. So let me label this as the equation number 1. And then now, let's just write this out in a more clear way. So in order to write this out, simply you apply the product rule. Well, now that you have the divergence outside, you have the product of the scalar function with a vector field. So maybe it's better for us to know some basic rule about the product rule for the divergence. So here's a quick note, which is the following. So if you take the divergence of a scalar function, let's say this is f, is a scalar function. So f is R2 to R. And now suppose that V is a vector field. So by the way, the product rule that I'm writing down is not just restricted for two-dimensional case. So this is true for any dimensional case, by the way. Okay, so divergence of this one. So first of all, the product of the scalar function and a vector field is another vector field, right? So it doesn't make sense to take the divergence of this vector field. And what is the result for that? Well, you just apply the same product rule as just, the derivative of the scalar function. What I mean by that is if this is taken on f, it becomes just a gradient. So you have gradient of f. And then the dot product just becomes the dot product with the v. And then now, if the divergence is acting on v now, this is truly becoming the divergence of v. So you have f times the divergence of v. So that's one. And well, this is really easy to check, right? So you just write out in the component form that one can easily check. Another one, before I just get back to here, so another one is that if you take the divergence of the gradient of a function f, right? Then, well, if I just write this out, this simply becomes, well, if you just apply the definition directly, for 2D case, and this is just phi, not phi. So d11f plus d22f, right? So by definition. And then we do have another differential operator for this particular type, which is called Laplacian of f, right? So I believe that we discussed about this on the first day, right? So this was one of the typical or simplistic example for the elliptic PD, remember, right? So this is the name of this is Laplacian. So, well, this is the notation that mathematicians prefer. And this is the notation that engineer or physicists prefer, because this is more physical in a way, okay? Just so you know. Okay, so now that we have these two rules, now we are going to apply these two to here. So if you apply the product rule, then this equation 1 now becomes, so you do the same business. So first take the gradient into here, right? Then you have the gradient of this one times gradient of phi, right? So that's the first part. And then if the divergence now finally hits the gradient here, then it becomes Laplacian that I just talked, okay? So this plus, it's a pity that I don't have enough space here, but we are going to just make some more room later. Times Laplacian of phi equal to 0. So now you can start seeing that obviously this is the, so the writing is not so good, but let's call this is 1 star now. So this is a more, the more kind of extended form. So now I'm going to write down further so that we can figure out the type of this equation, right? So just by taking from 1 star Okay, so now I'm going to write this in a component form. So which I will just leave all the detailed computation to you. So let me just write down the resultant form. So this one I can write out, okay. Let me just take the Laplacian first out. Okay, times Laplacian phi. Then if you compute the gradient of that, so that's going to become, just to check. So you can just check this on your flight back home, right? So when are you leaving? Tomorrow? Today? So tomorrow on your flight, just check, okay? When you're sleepy after lunch or something. Okay, so this is a summation ij equal to 1 to 2. So di phi, so dj phi, so dij phi equal to 0. So actually what I want to tell you is that this is truly a second order PDE and nonlinear, okay? So now we can figure out the type of this equation. And then it will turn out not that simple. All right, so if I just write this as a summation of ij equal to 1 to 2 and aij, so the coefficient for the derivative of dij phi, so let me just use this notation. Then you can see that the coefficient now is not a given function, but rather this depends on the gradient of phi, right? Okay, so let me be more precise. So if you look at the coefficient matrix, so let me just say A11, A12, A21, A22. So we have to look at the coefficient matrix now, right, to figure out the type. So you remember what we discussed on the first day, right? So you collect all the coefficient as a matrix, and you compute the determinant, and then you look at the sign of a determinant. The sign will tell you the type of the equation. So that's the whole story that we are trying to do right now. So A11, so I'm going to just write out right away. So this is just a tedious computation. So nothing really, truly amazing going on here. So that's the A11, right? Can you see why this is A11? Yeah? Okay. So then the second one. So for the A12 and A21, so those terms, so here there is no contribution from here, right? There is only contribution from here. So this is minus D1 phi, D2 phi, and in fact it's the same here. So this is D1 phi, D2 phi, and finally this is minus D2 phi square, so the matrix. So this is coefficient matrix. So just, well, this is a really huge expression. So let me just use the coefficient matrix A, okay? All right, so this is the kind of extended form of the potential flow equation. But well, at this point, this equation itself is already something very non-trivial. So we don't want to waste our time, precious time, just to talk about all the complications. So from now on, I'm going to introduce even further simplified potential flow equation so that we can just see the essence of the argument. So now, let me introduce a simplified potential flow equation. Okay, kind of a toy model, but this will be enough for us at the moment. So simplified potential flow equation. So by the way, so this is the equation that I studied for my PhD dissertation. Although I work for the n-dimensional case without any restriction, but this is the equation. So you can see that this is already very non-trivial to study. Okay, so simplified potential flow equation. Now I'm going to just assume that, so here, I'm going to just to remove this term to be 0. So we only consider the equation. So 1 minus this times d11 phi plus right? So this is still very non-trivial, we can see, right? Okay, and then for this one, the coefficient matrix, let us look at the type. So this is our A11. So let me just use this notation, and this is A22. So now you can realize that this equation is almost the same as the one that we have studied the day before yesterday, right? Except that now A11 and A22 are not just a function fixed, it depends on the solution, okay? So let us look at the type. So for that, we look at the product of A11 times A22. So if this A11 times A22 is a positive, then this is a simplified potential flow equation, which I will just use this initial. So this is, what is the type of that, if this is the case? So this is basically the determinant of the matrix, yeah? So if the determinant of a matrix is a positive, then the type of the equation is elliptic, right? So this is elliptic. And if A11, A22 is a negative, then this equation is hyperbolic. And this is the case that we want to consider today. Okay, so now, eventually what I want to do is to find a non-trivial solution for this equation so that the type of the equation becomes hyperbolic. But the interesting point is that you see the type of the equation is determined by solution itself. But theoretically, in order to determine the solution, you need to know the type of the equation so that you can analyze and find the solution. So this is a kind of a paradox in the study of nonlinear PDE, especially the coefficient depends on the gradient of the solution. So this is much difficult compared to the case where the coefficient depends on the solution itself. So when you talk about the nonlinear PDE, depending on how the coefficient depends on the solution, whether it depends on the solution phi itself or gradient, then you can also classify the type of the equation. So now the coefficient depends on the gradient. So if that is the case, we call the equation as a quasi-linear. So if you see this terminology, it means that, oh, the coefficient depends on the gradient, okay? All right. So from now on, let us talk about the hyperbolic solution. So start with the simplest case. So first of all, 1D hyperbolic equation. So 1D solution for a hyperbolic simplified potential flow equation, okay? So for that, now I'm going to assume that the potential function phi depends only on x1, okay? And then now I'm going to compute the one-dimensional solution for that equation so that it satisfies this condition, which will give us the hyperbolic equation, right? Okay. So let us just set the derivative of phi. Now this is the one variable function, so therefore we only have the ordinary derivative. So let us set this u to be just d1 phi. Well, in fact, this is just phi prime, right? And for this one, let us just write simplified potential flow equation in terms of U. So that then it becomes really simple. So now that we do not have this part, right? So we only have this part. So therefore, the coefficient now becomes 1 minus. So now here, both of the gradient of phi squared and d1 phi squared, they are same as just u squared, right? So this is 1 minus 3/2 u squared. And then d11 phi just becomes u prime equal to 0. So if you consider one-dimensional solution, it just becomes a nonlinear ODE. Okay, so this is the first step to study that equation. So we are going to start with something very simple, and then we are going to build up a new problem so that we can construct a multidimensional solution starting from one-dimensional solution. So that is our aim for today, if we have time. Okay. Can you actually, are you okay with this one? Yeah, good. Okay. How many solutions we have for this one? Without any initial condition, right? How many solutions can you find? Infinitely many, right? So either you can make this 0, right? Okay, but of course for us, making this 0 is much more interesting. But if u prime is 0, which means that any constant is a solution, right? But now I want to take a particular one so that the corresponding equation becomes hyperbolic. So here, now we simply take a solution. U, so let's talk about U first. So I'm going to make this to be just the particular constant 2. And you will see why I pick this one later. So just pick 2 for a certain reason. So then just back to phi, right? So here U is simply the derivative of phi. So therefore the corresponding solution phi x1 is just the integral of 2, so which is 2x1. And then let me just ignore the integral constant, which we don't need. So at the moment, what I'm interested is to just pick a very special solution for a certain purpose that I will reveal in a minute. So this is phi x1. So then, okay, yeah, this one I will keep. Now let me just give a name for this solution. So here's the definition. So let me just define phi bar x1, x2, right? Because I'm generally considering two-dimensional problem. So let us define this as 2x1, which is basically one-dimensional solution of this simplified potential flow equation, okay? And then we call this one, so this is called a background solution. So obviously, this phi bar is a solution of this problem, non-trivial solution. So in PDE, the terminology of a non-trivial is given when the object is non-zero. So this is obviously non-zero function that satisfies that equation. So we call this as a non-trivial solution. But still, this is one-dimensional. Now here's the observation. So let me just define or set the determinant of the matrix as M, as we did on our first day. So this is to be A11 times, well, but here, well, this is more, the important point is that now M depends on the solution, not just the independent function. So this is going to be a function depending on the gradient of phi. This is to be the product of A11 grad phi, A22 grad phi. And then we already know that if the sign of M is a positive, equation is elliptic. if the sign of m is negative, the equation is hyperbolic, right? So that's what I've been really repeating to say so far. So now then, let us compute the sign of let us compute m at the background solution, okay? So can you give me the number for that? So what is the value of that if you just substitute this one into here? So if somebody give me the answer for that, then you are following me well. Otherwise, it's implying that everybody is lost. So we have to take up, right? We have to catch up. So let's see. Can you give me the value of this m here? What do? Go back and substitute this one there and compute, right? Let's do it together. So it's your last day, so you are losing your energy, right? No? Tired? Not tired? Excited to go back home? Okay, so just maybe 45 more minutes, then you will be free. So okay, so A11. So let's see, grad phi bar. It's just a computation, right? Then this is what? So this is 1 minus. So now gradient of phi just becomes 2 times E1 vector, right? And then you take the magnitude. So this is what? 4. And you take half. So this is a minus 2. And this is what? This is another 2 square 4, right? So yeah, it's a constant, right? Yeah, it's not bad. So A22 is what? This is much, so something is not, yeah, you know what? I just took it too much, I guess. Oh, yeah. This is a wrong choice. This is going to give me elliptic PD, which I don't want. Okay, this is much better than this one. Then this is what then? This is, right? What about that one? This is? Okay. Am I doing right? Okay. Then the determinant becomes what? The product of those two. So that's negative. So that's what I want. I want hyperbolic PD for the background solution. Okay. So therefore, the background solution, so from here, phi bar yields a hyperbolic PD. Okay, but that's not what I want. So my final goal for today, the goal is to find or to construct. So this is where the real story starts. So I want to construct a two-dimensional solution phi that yields, that solves hyperbolic PD. So that's what I want, okay? And of course, how do I do that? And then I want to find such a phi so that it's sufficiently close to phi bar. Hopefully, this phi, if this phi is sufficiently close to phi bar somehow, then since phi bar yields a hyperbolic PDE, at least we could hope that this new solution also becomes a solution of a hyperbolic PD. Okay, so that's what I want. Okay, and then we find such phi. So we hope that try to find phi. This is a difficult part. Sufficiently close to our background solution phi bar. So this is where whole story begins. Okay. Any questions so far? All right. So now for that, now let us set up the nonlinear boundary value problem. And then we are going to discuss how to solve them. Okay? So for that, now the main problem is find or solve the equation. So the simplified potential flow equation d2 to phi equal to 0. Okay, now I need to be specific on the domain as well. So in the domain, omega, well, I'm going to use the same domain as before. So this is going to be a square. Okay, all right. So this is my domain. So here, x1, x2. So here 1, 1, 0. So this is our omega kind of square. And then the boundary condition. So I need a boundary condition over here, so which I will call as gamma 0. And then we are going to give the boundary condition on the side, on the bottom and top, which I will call gamma W as a wall boundary for flow, right? So the boundary condition on gamma 0. Now for phi itself, I'm going to give the same value as our background solution phi bar. Okay, but phi bar, by the definition, so here note that phi bar is just x1. So therefore, on gamma 0, the value is 0. So just note that this is the same as the value of phi bar on gamma 0, where the x1 coordinate is 0. Is it okay? Yeah? Okay, good. Now we need one more boundary condition, right? Because this is going to be hyperbolic PD. So D1 phi, so same setting as before. So now this is important. Then now I'm going to give this as the same value as our background solution. But it's just the same. But it's going to give me the same solution, which is not interesting. So now I'm going to add extra one. So that's going to be h of a function of x2 here. Okay? So this makes the problem two-dimensional, not one-dimensional anymore. Okay? And then d1 phi bar, where by definition this is just 1 plus h of x2. And then of course here I need to say something about h. So later I'm going to give some condition for h. Okay? And on gamma wall, now I assign the slip boundary condition. So that's going to be d2 phi equal to 0. So here the main observation is that, so generally here h, assumption is that h is a smooth function So this is smooth. So infinitely many differentiable, and all the derivatives are bounded function. Moreover, now I want to give very particular one. It's norm C4 on 0, 1. So you remember the definition of this norm, right? So we basically compute the derivative up to order 4 and take the supremum of all of them, right? Then add them up. Then that's going to give me the C4 norm. Now, this one is going to be less than or equal to epsilon, where epsilon is a small constant. Okay, so 4. A small constant, epsilon. And then how small does it need to be? Well, that we can only decide in solving the problem. That's the difficulty, okay? But we will just briefly discuss on how small this must be later. So this is the problem. So one observation that you already have from the setting is that if h is really a function of x2, then we can easily expect that a solution of phi must be a function of both x1 and x2. So it's not a one-dimensional problem anymore. So this is truly a PDE. Do you agree? Okay. So how do we solve this one? So that is our main question. And this is where the fixed point theorem comes in. Okay? All right. So how do we do that? Now, first of all, the conjecture. Before I tell you how we do that. So by the way, so here I need to tell you something. So just by show of your hands, how many of you are comfortable with this one? Or how many of you are not uncomfortable with this one? No, right? Okay. So if you think that, oh, I'm not following this at all, I have no idea what she's talking about, that's completely normal. So you don't need to feel bad about yourself, right? So because this whole story, I never discussed this to undergraduate. But my goal today is not to make you understand this completely. Maybe if you just remember even just 1% of what we have been discussing so far. Oh, so I remember, so somehow fixed point theorem is related. I don't know how, but somehow it's related. At least I can tell the difference between linear PD and nonlinear PDE. At least I know why nonlinear PD is difficult, something like that. Then if you just get just a brief idea of that, then you are very successful in this summer school, right? So the reason why I'm telling you is because I'm sensing people are really being lost. So, but I don't want to lose you until this ends. So just so you know, just enjoy, okay? So just enjoy the show that I'm doing, right? Okay. All right. So conjecture, back to the business. So our conjecture is that, like I said earlier, we are going to look at the case where h is a function of x2, but still epsilon small. So conjecture is that if epsilon is sufficiently small, then we can find a solution phi to this problem, so to our main problem, that solves a hyperbolic PD. So of course here I need to tell you what I mean by that we find the solution that solves the hyperbolic PDE, right? So of course what this means is that once we solve the problem, of course we are going to check the sign of determinant, right? So hyperbolic PD means that we are looking for a solution phi that satisfies the condition that this determinant of the coefficient matrix for that solution is negative in omega up to the boundary. So that's what we mean. Okay, so not only we are trying to find the solution for that problem, but also we are trying to satisfy that condition. So on the surface, it looks very difficult. So just to, solving this problem is one thing, but we have to also show that our solution satisfies that condition at the same time. This seems to be very difficult and very challenging. But in fact, what's going to happen is that we are going to use this condition to solve the problem. So that's the key. Okay? So now I will be more precise now. So especially if you have your boundary condition, which is a really, so this is a kind of, okay. So now with this condition, the fact that the norm of H is sufficiently small, which means that, if this is a 0, this is simply one-dimensional problem. And then we are simply adding really minor perturbation on the boundary condition, right? So this is called a small perturbation problem. So whenever you study nonlinear PD, you always start with a small perturbation problem. And once you can solve the small perturbation problem, then just you try to remove this assumption of the smallness of the perturbation. And then you just move forward, okay? So we are trying to find the small perturbation problem. So what do we do for that? So we just rewrite the problem in terms of the perturbation term, okay? So now let us define small psi, okay, to be the difference between a solution phi that we want to find and the background solution. And then we are going to rewrite the problem in terms of psi, okay? And for that, let me just also define the coefficient in terms of the gradient of psi. So let us set, so here maybe I will just use, what do I want to use? I want to use large A maybe, okay, ij of gradient of psi. So that's going to be small a, not ij, so here ii, grad phi bar plus grad psi. So what I'm just trying to do is that right over here, just to rewrite this as psi plus phi bar and just try to look the coefficient as just depending, as a function depending on the gradient of psi. Okay, is it okay? Just technical exposition. All right, then we can just rewrite the problem as following. The main problem can be written in terms of psi as follows. So first of all, we have A11 of grad psi, right? And then now D11 phi. So let us take a look at this. So D11 phi is D11. So by definition, this is psi plus phi bar, which is equal to what? Which is equal to just y. Phi bar is a linear function. So if you differentiate twice already, that disappears. Okay? So you have a D11 psi plus, and then you have A22 grad psi D22 psi equal to 0 in omega. Okay? And then for the boundary condition, now we have psi equal to 0. Also, d1 psi now, by definition, this simply becomes h, x2. Okay? And for the wall boundary condition, do we also have d2 psi equal to 0? Same as the previous one for original function phi. Is it true? Yes or no? Yes, why? Well, you know, same deal. So d2 phi is d2 psi plus phi bar generally, which is why? Phi bar is a function of just x1. Yeah, nothing difficult. So now if you can just rewrite the problem as a perturbation function, and then you can try to solve this one. So once you find the solution for this one, then you know psi, just put it back in here. That's going to give you phi, which is the solution of the original problem. Yes? Okay. Any questions so far? Don't be afraid to ask any question. Okay. So now, probably people will be waiting. So when this fixed point business comes in, right? Now it's going to start. Okay. So from now on, I will stop being very rigorous and then move on in a very heuristic level, because it's very difficult to be rigorous. Because you see, if you solve this problem rigorously, it's gonna take maybe 40 pages on A4, like the papers. Okay, so it's a long-term work. And of course, you are welcome to try to solve this one. Okay, this is a good problem. I will tell you the idea, and then you can try to solve this on your flight back home, right? And then you can try to finish before you arrive. Even if you can, you're gonna be the winner of a Fields medalist in maybe 20 years. Okay? All right. So the idea is the following. So heuristic observation. Heuristic observation. So first of all, well, now remember, whatever we do, we want hyperbolic PD. So how do we achieve the hyperbolic PD from here? Okay, so if the gradient of psi is just 0, we know that this is a hyperbolic PD already, right? So we can at least guarantee that if the size of a gradient is sufficiently small, very likely that the PD is still hyperbolic. Right? You can easily see from the representation, right? So that's the first observation. So so gradient of psi, so how do we put the size? We have to put the size at the C0 norm of a gradient of psi, right? If the size of this is sufficiently small, then equation over there, right, is hyperbolic. And we know how to solve, at least if the coefficient is fixed, okay? So that's the first observation. So therefore, now from there, so we try to solve that main problem by the method of iteration. So now I need to tell you what I mean by the method of iteration, okay? So this is where you need to know the theory for linear hyperbolic PDE. Okay, so method of iteration. What I do is just try to find the solution by making a right guess. Okay. So what do I mean by that? So I introduce so-called iteration set. Let's iteration set. So that's going to look like something as follows. So I'm going to use the notation I. And that's going to be a set of functions, okay, which is the function from omega closer to R. And now I want to make this I is a set of all functions that can possibly solve the main problem. That is called iteration set. But this is absurd, right? If you don't know the solution, how do you know that which function can possibly solve that problem, which function cannot, right? So the idea is the following. Well, since we cannot just pinpoint any particular analytic property for the functions that can possibly solve that problem, I just make a rough guess. All I need to do is to collect all the functions that can be possibly, the size is very small because I'm solving the small perturbation problem, right? So here I only expect that this size to be very small. But you know, when you talk about the function, the smallest can mean a lot of different things, right? It can be small in C0. It can be small in L2. So the real question is, where do you want your function to be small? In which space do you want your function to be small? So we have to pick a correct space. So this is the real challenge. So if I can make a correct guess on the space of solutions, space of functions that can possibly solve the problem, then I'm in the good start, okay? So now this iteration set is going to be the set of all functions so that it's a norm, but I don't know what the norm is. That's the problem. Whatever the norm is, this is small here, okay? So here, sigma is a small constant. Small constant. And then here, B is a Banach space. But I don't know what space to pick, so this is a Banach space to be determined. And how do I determine that? I can determine this by making a lot of heuristic observations. That's what I'm trying to do here, okay? So, and then this also concerns the application of a fixed point theorem that you already learned yesterday, okay? So I don't know what the Banach space is, but for whatever the Banach space is, I want the collection of all functions so that their norms in this space is sufficiently small. But I cannot just pick any space, right? I have to make a good guess. That's what I'm doing here by heuristic observation, okay? So here the question is, how small sigma must be the sigma must be. Also here, one other thing is this h, right? So at the beginning, we assume that the norm of h is small, but we never said how small it must be too, right? So this also is related with the question of how small the norm of h must be. Okay, so that is the first question, the question number 1. The question number 2. So what is this Banach space? Okay, that's question number 2. So once we figure out that, then we can start applying so-called fixed point theorem, then we are done. Any question? So now for the rest of the time, it's about 20 minutes, I'm going to tell you what kind of observation we have to make. And then based on that, what can you do to solve this problem in terms of the method of iteration? Okay, all right. So back to this heuristic observation. Now let's talk about this in terms of this iteration set. So for any given phi, now I want to consider, I really don't have enough space. Maybe I'll erase this. So now we are going to fix phi, right, in this iteration set and consider a linear boundary value problem of the following. So for this equation, so we get A11. So just to compare with this nonlinear problem. So the reason why this is difficult is because the coefficient depends on the solution. So our strategy is to replace this part by something that we can fix. So we are going to replace this gradient of small psi as gradient of phi for a fixed function in the iteration set. So let me tell you the strategy first, okay? So then A11 grad phi and D11 psi. So this is going to be something different. So let me say just big psi and A22. So this is a linear boundary value problem for big psi, okay? Not small psi. So A22 grad phi D22 big psi equal to 0 in omega, okay? And then the boundary condition is going to be same. So on gamma 0, we require that big psi to be 0, and D1 psi is h. And on the wall, so D2 psi equal to 0. So this is going to be the linear boundary value problem associated with this big phi, okay? So for each choice of function phi from the iteration set, you get a linear boundary value problem. And before I get into any further on these questions, so let me briefly explain how we can solve that nonlinear problem by solving this problem, okay? The idea is the following. So this is a method of iteration. Maybe this is a better way to approach. So first of all, you fix phi and solve this linear boundary value problem of phi, okay? So here the thing is the following. So based on what we have learned for the last 2 days, 3 days maybe. So this is what I want to say. So if the gradient of phi is sufficiently small, then like I said, this equation is going to be hyperbolic. Do you agree? So therefore, this is exactly the same linear hyperbolic PD problem that you studied for the first 2 days. Okay? So then, this linear boundary value problem associated with phi is hyperbolic. Okay? Then we can solve. So then now we can introduce a kind of infinite dimensional mapping. So now we define, okay, so if for any given phi in I, right, this is the thing. If for any given phi in this iteration set, if the smallness of a phi in this Banach space implies that the smallest in the size of a gradient. So that is the first clue on how to fix the Banach space B. So when you pick the Banach space B, you should do so that when this condition is given, by fixing sigma sufficiently small, you should be able to show that the gradient of a phi in C0 is sufficiently small. So for example, this B must include C1, right? For example, so it could be C1 or higher, right? C1 or C2, something like that. So that's how you start guessing or building up the properties for the Banach space in your iteration set. Okay? So then for this hyperbolic problem, if for any phi, one can find a unique solution psi to the linear boundary value problem phi. So this is where you use your knowledge from the first 2 days, right? Then we can define a mapping, and this is called the iteration mapping. Iteration mapping, which I will write as this script of f. Okay, so this is going to be a mapping from iteration set. And hopefully this will go to maybe the Banach space that I'm using here, okay? So that I fix any phi, then I map this to the solution psi. Okay? So then we can define an iteration mapping that way. But there is one condition here, right? So this mapping really can map this iteration set into this Banach space only if I can guarantee that this big psi really belongs to this space. So it means that the Banach space must be correctly chosen. For example, it cannot be like C infinity or something, right? Because if your coefficient, for example, is in C4, you cannot get your solution to be infinitely differentiable because the regularity of your solution completely depends on regularity of a coefficient. So this is the difficult part in studying the nonlinear PDE. Because on our first 2 days, when we define our linear boundary value problem, we simply define the coefficient as smooth. So we didn't need to worry about, our solution can be bad just because of a coefficient. But when it comes to the business of a nonlinear PD, it's completely different situation, right? Because how nice your coefficients are completely depends on how nice your solution is, and vice versa. So this is the difficult part in choosing like the correct choice of the Banach space B. Isn't it wonderful? That's the mystery in the life, right? Okay. So here you need a really deep understanding deep understanding of linear PD theory is required. So when we say deep understanding, now you really have to consider more general case in terms of, oh, if the coefficient have a bad regularity, then how your solution is going to be bad in terms of regularity, right? So you have to really study the close relation between the regularity of the coefficient with the regularity of the solution. That's the beauty that you have to learn from linear theory. Then you bring back to nonlinear theory and start the iteration process. Okay? All right. So then what can we do with this iteration map? Well, now let's try to connect this F with our nonlinear problem. So this is the really punchline. So if an element phi star satisfies that, so when you just map phi star by iteration mapping, if it turns out that this is phi star, then phi star really solves the main problem here. Can you see why this is the case? So let's see. If this is the case, you just bring back into here. So here, you just fix your coefficient as gradient of phi star. And by the assumption, then we have D11. So in the position of psi, we have a phi star here, right? And then here, same. Okay. And the same for the rest of the boundary condition. So this phi star exactly solves this nonlinear boundary value problem. Is it clear? So, punchline. If phi star is a fixed point of this iteration mapping, then it becomes a solution of this original nonlinear boundary value problem that we desire to solve. So therefore, in this strategy of method of iterations, the real difficult part is to find this particular point that satisfies this property. And for a given f, for a given mapping f, right? Any element satisfy this property is called the phi star is a fixed point of the mapping, iteration mapping F. So once you set up the iteration mapping, right, the remaining question to solve this main problem is to prove whether your iteration mapping has a fixed point. So this is where you need to apply the fixed point theorem. And then, in the world, there are so many different types of fixed point theories. Which one to pick? completely depends on the style of the problem and the regularity that you have. So if your iteration set has really good regularity, it's better to pick a fixed point theorem that requires a strong condition and yields a strong result, such as a contraction mapping principle. So now, so for the remaining time, I will talk about two different types of fixed point theory, and I will try to explain the difference between them. Okay? So is it clear so far? So I hope that at least I could give you a clear motivation to study fixed point theory in the future. So if you know more about the fixed point theorem, you should look at any textbook on functional analysis, okay? All right, so now, let's see. So, well, I know that you learned two different types of a fixed point theorem yesterday. Yeah. Good. Since we only have very few minutes, maybe I will try to explain. The easier one and the strongest one, which is contraction mapping principle. Okay. So. Because this is the one that everybody wants to apply, if possible. And let me tell you why. So contraction mapping principle. Okay. So this one says the following. Suppose that you have a mapping F. It's very simple. So if F from a Banach space, so this is a Banach space. So if you apply contraction mapping principle for your problem, this Banach space could be the same one that you have here. So that's why this is so convenient. Okay. So if F maps a Banach space to itself, right, at least it should have the same domain with the target space so that you can have a fixed point. If F satisfies the following, that you look at the distance between, so f of, let's say, phi1 minus f of phi2 in the norm, right? So this is the difference of the image in the Banach space. If this is, maybe I will just better to state this way. So if there exists a constant mu less than 1, a constant such that the mapping satisfies that this is less than or equal to mu phi1 minus phi2 in the space B, okay, then F has a unique fixed point. In B, okay? So not only this guarantees that the mapping has a fixed point, in fact, the fixed point is unique. So if you can apply this contraction mapping principle to our problem, if that is the case, then not only you just to prove that your nonlinear problem has a solution, but also the solution is unique. So you can actually prove the existence, uniqueness simultaneously. So that is the really powerful point of the contraction mapping principle. So this is how the study goes in general in the nonlinear PD business. So whatever you do, always you start with this small perturbation. Then you set up this method of iterations. So then you have to make a choice on which fixed point theory to apply to solve the problem. The very first thing that you attempt is contraction mapping principle for everyone, because that gives you the strongest result that one can imagine. So you try. If you fail, because this can easily fail, because it's really strong condition to achieve. This is the problem. This is the nice property, but very strong. Strong is strong property to achieve. So strong, very hard to achieve. Yeah, that's like the two sides of the life, right? So if you want something big, you have to sacrifice big. So sometimes it works, sometimes it fails. In this case, works if you choose the correct choice. So somehow, the choice of a fixed point theory coupled with the choice of the Banach space in the defining iteration set. So they always go together. So it's not like a one-way traffic. So you really have to work from many directions to work things out together. So this is the difficult part. So if the contraction mapping principle fails, then you go to other fixed point theorem. And that alternative choice could be, for example, shadow fixed point theorem. But if you remember what you learned from the recitation session yesterday, the shadow fixed point theorem only can guarantee the existence. But you know, normally when we study the PDE, we just wonder, does solution exist? If it exists, is it unique, right? Unique, non-unique is completely different story, right? If you have non-uniqueness, then you have to analyze why is it non-unique? Is it because the boundary condition is wrong? Is it because the equation is wrong, right? Physically speaking. So if you, for the shadow fixed point theorem, you get the existence, for example, then does it mean that you failed to achieve the uniqueness? Well, not necessarily. Then there is alternative way to check the uniqueness in that case too. So this is where all this complicated works begin. All right? So result is so difficult, therefore so interesting. So that's my conclusion. So I guess that's it for me. So everybody have a safe trip back home. Yeah. So I hope you have a good time. Okay. That's it. Okay. Thank you.